Hello everyone, welcome to video lecture series of design of steel structure. We are dealing with unit number 4, that is the design of flexural members, and in the previous video we have seen introduction to laterally unsupported type of beams. So that is when any lateral restraint is not provided to compression flange of your flexural member or I section, and this particular I section is subjected to torsional buckling along the length of beam. In that cases, these beams are categorized under laterally unsupported type of beams. So in the present video, we are going to see numerical on analysis and design of your laterally unsupported type of beams. So the numerical statement for given laterally unsupported beam is: it is design a laterally unsupported I section beam with simply supported ends of an effective span of 6 meters and subjected to working imposed load of 35 kN per meter. Assume that full torsional and warping restraints are provided at support. So already discussed in the previous video, this particular statement or last line from the statement of your numerical is giving us effective length. So table number 15 is to be adapted to calculate the effective length. As in case of laterally unsupported type of beams, initially table number 14 is to be adapted for calculating FCRB value, which requires slenderness ratio KL by R value and H by TF ratio. So for that KL by R calculation, they are mentioning it is full torsional and warping restraint provided at the support. So based on that, table number 15 is to be referred and effective length Kn can be calculated. The next given data, it is a I section and it is simply supported for effective span of 6 meters. It is subjected to working imposed load of 35 kN per meter. Now again here you need to understand it is a working load and uniformly distributed working load is 35 kN per meter. So this particular given value is to be converted to factored loading. Again here you can see that there is no data is mentioned regarding the self weight of your beam section. So again certain value of self weight of beam section is also to be assumed. So this is the beam cross section. Given data span is 6 meters, simply supported, UDL working is given 35. So as load acting mentioned in the numerical is working load without self weight of the section, you will assume certain value in the range of 0.55 kN meter to 0.95 kN per meter. So we'll go with 0.85 value. Therefore now total loading will be given loading 35 plus 0.85 value. So assumed value is 0.85. Therefore your total loading will be 35 plus 0.85 multiplied by partial safety factor 1.5. Now I am getting total value as 53.775 kN per meter for an effective span of 6 meters. That is nothing but 6000 mm. Now next is maximum shear force and bending moment calculation. So according to discussion in the introductory lecture, standard cases, that is simply supported condition with UDL, maximum bending moment will be WL square by 8 value and maximum shear force will be W into L by 2 value. So maximum shear force we are getting as 161.34 kilonewton and maximum bending moment we are getting as 242.01 kilonewton meter. Correct? So shear force diagram will be likewise. This is the shear force diagram, 161.34 kilonewton on both the sides, reaction at A point and reaction at B point, and this will be your bending moment diagram. WL square by 8, maximum moment at the center span, that is L by 2, 3000 mm, and the value is 242.01 kilonewton meter. So your beam is to be designed for 161 factored shear force and 242 kilonewton per meter bending moment. Now initially plastic section modulus for your trial section is to be adapted by equating your design bending strength with maximum bending moment. So maximum bending moment is known to us 242.01 into 10 raised to 6, and that is to be calculated with plastic section modulus into FBD value. Now here the slightly change in the formula is there. So for calculating value plastic section modulus by assuming your FBD value. So here for rolled I sections you assume FBD in the range of 120 to 130 or 140 sometimes. For that value your plastic section modulus required is 1.86 into 10 raised to 6. So for this value you need to select a section from annexure H IS 800. So suppose I will try ISHB 450 at the rate 87.2 kg per meter having properties are. These properties I have directly taken from steel table. Depth of section, width of flange, thickness of web, moment of inertia about major axis, H1 value, RZ value, RY value, plastic section modulus and elastic section modulus. All these values are directly taken from steel table as these are required to calculate the strength. The next is important is classification. So according to table number 2, classify your cross section as plastic, compact, semi-compact or slender. So again here from this observation we can tell that the section is plastic and beta B value is going to be 1.0 as our values are within the range of first class, that is your plastic section. So directly we can tell it is a plastic section and beta B is going to be 1.0. The next is design shear strength of your section according to clause 841 page number 59. Design shear strength is to be calculated by consideration of your web area, and in case of rolled section web area is overall depth multiplied by thickness of web. So FYW into AW root of 3 divided by gamma m0, and we are getting answer as near about 560.94 kilonewton. So the capacity of your web to bear shear force is, or to take your shear force is 560.94 kilonewton, and this is almost equal to greater than your maximum shear force 161. Now after this we'll go with high shear and low shear condition. So check for high shear and low shear condition 0.6 VD value. So calculated answer into 0.6 we are getting 336.56, and again this value is also greater than maximum factored shear force 161.34 kilonewton. Therefore it is a low shear condition. Now design bending strength for low shear condition in case of laterally unsupported type of beams, that is beta B into ZP into FBD. So already in the previous introductory lecture we have seen how to calculate your FBD. FBD depends upon table number 14, and that is initially you need to calculate your maximum slenderness ratio KL by R and H by TF ratio. So for calculation of FBD, that is design bending compressive stress due to torsional buckling, critical stress FCRB is to be calculated first. Now for calculating FCRB, we require slenderness ratio KL by R and H by TF ratio. So H by TF ratio we are going to get directly from the cross section, and lambda value KL by R is known to us from effective length divided by least radius of gyration. So effective length KL is 0.7 into 6000. From table number 15 we are referring, page number 58 for normal condition. So KL is 0.7 into 6000, that is 4.2 meters. And referring table number 14 page number 57 of IS 800 we get. So these are the values for KL by RZ. Now this particular slenderness ratio purposefully I am calculating for both the axis, that is major axis and minor axis, that is lambda for Z side and lambda for Y side. So that will be KL Z by RZ and H by TF value, and second will be KL Y divided by RY and again H by TF. So here double interpolation is to be done. For H by TF ratio 32.84, that will be common for both the sides, and KL by RZ value. Now here your radius of gyration about Z side is different and Y side is different, therefore these two different tables I have considered. So initially I am getting value of 22.36 which is in the range of 20 and 30, and 32.84 is in the range of 30 and 35. So these values are going to be common for second calculation also, only there will be change into KL by R value for both the conditions. So these both conditions we are going to calculate, but we are going to consider the least value because higher value is going to give us greater FBD strength. So for rolled section already we have discussed alpha value is 0.21, and based on that FCRB for first calculated value 4768.70. This is the final FCRB calculated. For this you are calculating FBD. So and for second calculation also your FBD is to be calculated. Now by observing both the values, that is 227.3 and 179.52, these both are going to give us strength, that is bending strength for laterally unsupported, but we are going to consider least value, because if least value is going to satisfy the design strength requirement, in that cases this higher value is ultimately going to satisfy. So according to that your design bending strength for laterally unsupported beam is equal to beta B is equal to beta B into ZP into FBD, and the value we are getting near about 351 kilonewton meter. So 350.96, which is almost equal to 351. Therefore, your maximum factor bending moment capacity of your section is greater than bending moment acting 242. Therefore, the section is safe. It is okay. Now, similarly, go for your design check. Initially, web buckling check. Now, for web buckling change, your FCD value is to be considered, and FCD depends upon KL by R value. Now KL by R value is always 2.45 H1 by TW, that is 96.55. For this buckling class C and lambda 96.55, directly calculate your FCD value, which is almost 111.83. Now remaining is the point of B into thickness of web, that is area. B we are going to assume. So B is assumed in the range of 100 to 150, and TW is nothing but depending upon your dispersion angle, and we are calculating that dispersion angle for only single dispersion. So single dispersion value is H1, and H1 we are going to get directly from your from the depth of your section. So by considering that value, calculate buckling strength FWB, and this is equal to 343. Again, this value is greater than maximum shear force, therefore it is safe. Similarly, go for the next one. Check for web crippling by considering Fy as 250, and this particular Fy calculation is directly to be considered, and for your area value, your dispersion for reaction is to be considered, and that depends upon thickness of flange and R1 value and slope of 1:25. So similar calculation we have done for previous problems also, just there is assumptions of your plate bearing width value and direct calculation you can make. So here you can observe that almost we are getting value as 427.07 kilonewton, which is greater than your maximum factor shear force. So again, your selected section is safe for web crippling as well as web buckling. And last is deflection check. In case of simply supported with UDL, maximum deflection is given as 5 upon 3 5 WL raised to 4 upon 384 EI. So here W value is your working load, and working load according to statement is 35 kilonewton per meter. L value is known to us, and your E value, that is modulus of elasticity 2 into 10 raised to 5. I value is moment of inertia about major axis. So putting all that value, you are getting deflection according to loading is 7.53 mm. So if the loading of 35 kilonewton per meter is applied, it is going to give us deflection of 7.53 mm. This is actual deflection, and this actual deflection is to be checked with the maximum limit as per IS 800. So maximum limit is span by 300 to span by 240. So that is, it should be in the range of 20 to 25 mm. This is the maximum allowed deflection, and we are getting according to loading as 7.53. Therefore it is within the limit. So in short, your selected beam is safe for web buckling, web crippling as well as deflection. So from this only you can go the statement as ISHB selected 450 at the rate 87.2 kg per meter can be used for given loading as it is safe for all the checks. So this particular last statement is defining that selected section is satisfying all the criteria. All the criteria in the sense its design bending strength is greater than maximum bending moment. Its design shear strength value is greater than maximum factored shear force. It is safe in web buckling FWB. It is safe in web crippling and also for deflection. So this must be your summary of the numerical in case of laterally supported or unsupported type of beams. Difference in calculation is only for laterally supported type, torsional or elastic torsional critical moment is not considered, which is considered in case of laterally unsupported type of beams. So here the numerical is completed for your laterally unsupported type of beams, and these are subjected to lateral elastical torsional moment. So shortly we will just recall the statement of the numerical. So statement was given, loading was mentioned. In loading, your working load span of the beam was given, and based on that you have calculated maximum bending moment and shear force, and for calculated values you have selected a section, and that selected section is now satisfying our conditions, that is for all the checks adapted, and we have defined that the given section selected, that is IS HB 450 87.2 is satisfying the given criteria. So here the numerical is completed. In the next video we are going to see analysis type of numericals on laterally unsupported type of beams. So there will be two types of numericals, design type of numerical and analysis type of numerical. So this particular numerical was rated with your design type as loading was mentioned and you have identified the cross section. In analysis type of beams, your cross section will be given, and for that cross section what can be the maximum uniformly distributed load or external load that can be applied in order to be the beam in safe condition, that is to be calculated. So that numerical we are going to see in the next video of analysis of laterally unsupported type of beams. So thank you.